Okay, so I'm going to talk about, well, I'm going to firstly talk about a specific problem which is faced in many developing countries, in the power networks in many developing, although not all developing countries. I'm going to zoom in on a particular problem which has to do with the sort of daily operation of power networks. And I'm going to, which you will find in lots of countries, but I'm particularly then going to zoom in on the Nigerian context. I'm going to talk about a sort of early, very preliminary piece of work I did, which was about trying to model the challenges faced by a system operator trying to manage a grid in this kind of context, and then look at a more sort of future piece of work based on some data we'd obtained about a specific electricity distribution company in Nigeria. I guess the first thing I'll say is to get a bigger picture about the sort of energy systems kind of environment in lots of developing countries, you might be better off talking to Colin or someone with a wider expertise than me. But what I'm going to talk about particularly is this idea that many power networks in developing countries are essentially in a state of kind of constant power shortage. So I know this is the case in somewhere like Angola, in Nigeria, and in Pakistan, where the level of the sort of power demand connected to the power system is at all times of the day in excess of what the grid is able to deliver. So one essentially has kind of load shedding going on at all times as a sort of first resort in order to balance the grid. So it's not just a sort of last resort thing you do, it just has to be done at all possible times of the day. So you often don't really even know exactly what the peak demand is on a system like this because it's never met. We just know that it's somewhere in excess of what we're currently doing. So you end up with, instead of a sort of normal load duration curve with some sort of peak demand, which is during the day, and off-peak at night, your system is just operating at its pretty much peak capacity all the time and just rotating the set of loads which are connected. I'm going to talk particularly about Nigeria because I have a kind of relationship with a company based in Edinburgh that do a lot of consulting work with companies in Nigeria, and so we have reasonably good data access there. There we go. So the Nigerian power system was privatized, for good or for ill, about 3 years ago, and is essentially structured like this. So you now have privately owned generation companies owning generation assets, which are mostly gas-fired turbines. You have a combined kind of system operator and transmission service provider in this entity called TCN, the Transmission Company of Nigeria. And then you have lots of distribution companies, which are all regional monopolies, which do all the retailing of power in any particular area, but they don't tend to own any generation. And they retail power to consumers, and all the sort of transfers of money here are at kind of, even though it's privately owned, it's not really a fully liberalised market. These are all regulated tariff rates. And a side issue that I won't touch upon, but I'll just mention, is that generally these regulated tariff rates aren't sufficient to actually cover people's true costs. So there's an ongoing problem of lack of maintenance of all the assets in the system, which leads to very poor reliability. But that's just an aside thing. This is just to show you the physical structure of the system. So this is a map of Nigeria showing the high voltage transmission and generation on the system. And each of these regions that are highlighted there corresponds to a distribution company region. So those are all the little regional monopolies which are being supplied power by this wider transmission system. So one of the convenient data sources we have got access to is some operational data from the system operator, just showing how successfully they were at managing the grid. So this is just a sort of time series of the average output of the whole power system since about 2013, which shows these sort of generally is very jagged. That's largely due to this sort of poor maintenance I mentioned, which means that the overall level of available capacity on the system varies widely due to turbines coming in and out of service. And those bits where it goes right down to 0 are regular total system collapses, which has the result that, so this is a sort of similar looking time series, which is the average daily available capacity. So that sort of is part of what's limiting the power supply to consumers, although the actual transmission system itself is also constrained. So it's really a multiply constrained system. So the reason I was sort of touching on that is just to give an overview as to what one of the difficulties is for the system operators, so the transmission company of Nigeria. So I'll just briefly go back to this chart again. I was talking before about the sort of the flows of kind of money and what the main actors are in this system. I'm just going to briefly talk about the kind of left-hand side of that picture with the green arrows, and roughly how this system is controlled. So essentially what the system operator would have to do in this situation is every day or every hour really, they look at how much available generation there is, how many generators haven't packed in, how many of them actually have a reliable gas supply and are able to generate. They know they're going to use all of this because demand is going to be in excess of that. And they then instruct the generation companies what they want them to do, and then they also instruct the distribution companies how much load they want them to consume. And then it's the distribution company's job to hopefully do what they're told. That is to say, of all the available loads they have, all the available consumers, they're switching feeders on and off in order to rotate the connected loads, give everyone a connection at some point, and mean that the sum of all the connected people, the load should amount to what they've been told they're going to do. And of course, it doesn't perfectly. It sort of steps up and down every time they switch someone off or switch them on. And then somehow the generators are going to be following the load. So sort of first thing we wanted to do was just to sort of get a sense of what the kind of limits the transmission and generation system imposes upon what kind of distribution of power is actually feasible and how much can be delivered by this system. So in this piece of work, we essentially had access to a model of the power system, a sort of single-phase equivalent system model. And then we have lots of generation scenarios from the operational data I was showing you before of how much generation was available on any given day. We assume that the distribution companies are both able to do what they're told. So if I tell them to consume 110 megawatts, they actually can do it, and that they're willing to do it. So their incentives are right that they do connect what they're told to do. And we also kind of assume that load, even though in reality it's switched on and off in these discrete blocks, we just assume you can shed it as a kind of continuous variable. And then we can see what distribution of sort of what's the minimum total load you can shed in a particular case. You can also see what the constraints are on supplying load to a particular distribution company. So essentially this is set up as a kind of optimal power flow problem where you just, rather than choosing try to supply fixed loads at the lowest possible cost, we just allow yourself to shed load and have in the objective function some benefit of supplying load. And you can either supply as much as you can, or by tweaking things in that objective function, I can, for example, look at what happens if you try to supply as much power as possible to one particular distribution company region, where are the main constraints stopping that. We also analyse one particular policy which the regulator imposes in Nigeria, which is they want, because there's a limit on how much power you can supply, everyone wants more, they stipulate that each distribution company should receive some fixed proportion of the power which is available. And we essentially, we can sort of incorporate that target into the objective function and say you supply as much load as you can, but do it in this proportion. And we're able to show that this is, to some extent, isn't really feasible. If you really were serious about supplying load in these constant proportions, you actually have to sort of arbitrarily scale some people's load down in order to achieve that. So I'm going to, I think, skip over some of these precise charts of those outputs, but there's a sort of working paper on those, which if anyone's interested, I can share with them and get into the details of the sort of next piece of work, which is based on kind of questioning these assumptions here. Whoops, oh dear. Questioning this sort of preliminary assumption we made, which is that distribution companies are able and willing to do what they're told when a system operator tells them how much they ought to consume. So through some contacts with one of the distribution companies, this place called Yola Electricity Distribution Company, which is in the northeast of Nigeria, we've been able to get access to some basically very good data on what the sort of connected loads are and how they operate their distribution network. So that's just a sort of schematic of their whole network. So this is a preliminary kind of summary of what was sort of going on in Yola during the month of January 2016. So that blue line corresponds to what they were told they ought to do by the system operator. So the system operator, every hour, I think they literally send them a text message and tell them, we'd like you to connect this. This is how much power you're allocated. And then their job is to connect various feeders in order to do that. That red line is the actual consumption, power consumption, which the system operator metered for that region. So obviously at the beginning of the month, they were struggling to get up there, even though we know that the actual load, if you did connect everyone in that region, would be much higher than that. Although later, towards the end of the month, they were getting a little bit closer to it. So to try and explore that further, we sort of went back to Yola and asked them if they could actually give us sort of slightly more, less aggregated data. And they came up with this. So these are, so each one of those time series represents one of the 30 distribution feeders on their network. So this is the loads at the level at which they're actually managing who's connected. So what they're doing is that these are the people that where the switches are, and they're switching them on and off and deciding whether they get power. The huge gaps in those time series, because this data is over about a year, correspond to just where the entire set of data is not available. So that's not the load shedding. But within each of those lines where you have these kind of hourly recordings saying this is what the power flow was to this area, within there are gaps in the data which are caused not because we just don't have the data, but they're caused by the fact that they are load shedding. So this is just zooming in on one particular feeder in August. So where we actually have a specific reading of the power flow, there's a little line, and that shows the variations in power over the course of the time. And every time it goes red, that means we don't know what the sort of demand was there, because for one reason or another it was disconnected. So roughly six. This one's quite good, but on average, about 65% of the time people here are connected. About another 20-25% of the time they're load shedding because or maybe 20% of the time they're load shedding because they plan to shed load. And the other times it's off for some other reasons, which is often indicated in the data as like it was planned maintenance, it was unplanned disconnection. They say things like and all sorts of other reasons. They just had to, as an emergency kind of contingency, shed load when they didn't want to. So the previous chart I showed you when it was aggregated load for the whole distribution company doesn't really show any kind of seasonality. It's just all over the place, and it's not really predictable based on the time of day or anything. But if you take each individual feeder and then for every hour when they are connected, take the average load, we can produce these little sort of kind of profiles, load profiles for each feeder. So there's 30 of them in total. They're coloured by a sort of administrative thing. And it starts to look more like what you'd expect electricity consumption should, with a sort of, a peak during the middle of the day and then an off-peak period at night. So the role of what the distribution company is doing is they're essentially, at any given hour, they're choosing some subset of these feeders, which they are going to connect, and that the sum of their sort of power consumption shouldn't exceed what they've been told they're allowed to consume. but they'd want to consume as close to that as they can because they're only going to get paid by their customers for things they actually delivered. So what I would like to do with this, and I haven't done yet, is to sort of study these kind of time series of the demand in this area in Nigeria, and to see whether can we impute these kind of missing values. So where there isn't, those hours of the day we didn't know what the load was because they weren't connected, I imagine there is some kind of underlying demand process which would tell you what they would have consumed had you connected them. So can we then both impute the missing values in those time series and then subsequently kind of forecast individual feeder loads into the future, so hour ahead, day ahead, possibly based on other sort of local information like what the weather, the heat is likely to be, so how much will people have their air conditioners on. Is it possible we can then use that to come up with a slightly better load rationing schedule? I have to be quite tentative here because I think that it may be possible if you've got with some sort of to choose a load rationing schedule that provides consumers with perhaps a slightly more, at least more predictable connection, if not a less intermittent one. Their connection is always going to be intermittent because there's just not enough power. But it might be possible to choose some load rationing schedule which is more, at least more reliable. Although that will probably require us to kind of start to answer this sort of question, which is, does the load on an individual feeder change, bearing in mind they've been disconnected? So the obvious thought there is that if you disconnect someone's load during the morning, then the consumption they would have done in the morning, they might put off until the afternoon. And so, you know, you might need, if you wanted to somehow do better than the current schedule, which is not bad, you'd need to take that into account. So you need to sort of study this question of how people's consumption patterns are affected by the load shedding that's happened in the past. And that's where I'm going to conclude it for the time being. So if anyone has any questions, please feel free to ask them.
This production is brought to you by the University of Edinburgh.